Hello, my name is Joren Kirsis.
And I'm Skylar Dawson, and this is the Robotic Vacuum Redesign. So we used disruptive technology, failure mode, effective analysis, and eco-design to redesign a modern robotic vacuum system. And we redesigned some complaints that we found online. Some of these complaints were the battery life, the mobility, and also the noise produced from the robot, and we seek to improve all three of these in our design.
So for this project, we analyzed three different types of customers. They're the underserved customers, the overserved customers, and the not served customers. So the underserved customers are the ones that are completely satisfied with the products, the form, and the function of it. The overserved ones are where the majority of the complaints come from. So that's going to be the people who are going to be complaining about the noise, the battery life, the fact that the robot will get stuck a lot, and the not served customers. And these are pretty much the people that just don't have it.
And then to solve these problems, we want to create a model of the robotic vacuum that will operate effectively without the user's intervention and produce minimal noise from the vacuum. And then, so for the failure mode effective analysis, we found possible effects that could happen or the robot could fail, is if it was getting stuck or if it drove off a ledge that it didn't detect. So to solve these problems, we'd want to add better wheels to help with mobility on different surfaces, and as well as improve the AI of the robot so that it can detect these locations where it may get stuck and avoid those locations. And then also we found ways to improve the battery for if the battery ran out. We could improve this by increasing the efficiency of the system or using a larger battery. And to use a larger battery, we wouldn't necessarily want to add a heavier battery, but we want to add a more energy dense battery that would hold more charge rather than take up more space on the robot.
For our vacuum robot redesign, there are 5 specific constraints that we wish to meet. The first constraint is that the robot must be able to operate for at least an hour without charging, which we find is very, very reasonable. The second constraint is that the vacuum must not produce over 60 decibels of noise. The third constraint is that the cost of the robot must not exceed $100, or competitor robots might just be might just dominate us on the market. The fourth constraint is that the robot must be able to clean the area with over 80% efficiency. And the fifth constraint is that the robot must be able to clean a 10-foot by 10-foot open area within 10 minutes.
So here's our level 1 decomposition. And so to increase the battery life, to increase the battery module, we could use a sodium-ion battery, which is a more energy dense and also more eco-friendly alternative to lithium-ion batteries. An automatic charging dock is basically another solution where the robot could charge if it gets low on battery, it could automatically go and plug itself in. A larger battery would increase the storage size, but it would also increase the weight of the robot, which would also decrease the efficiency of the energy that used. To improve the vacuum, to reduce noises, we'd want to alter the suction of the vacuum, and also we could change the brushes that would affect the efficiency as well as the noise produced. Increasing the efficiency of the CPU, we could have the robot send status notifications to the user, as well as allow the user to operate the robot remotely, and the robot would be able to traverse its surroundings by mapping the area. And improve the motors and the mobility, we want to improve the wheels and how much traction they have on different surfaces.
For the budget of this project, we estimated the general cost of all the different components, like motors, vacuum, CPUs, batteries, etc., etc. And the prices sourced are, for the top end components, they have room to be more cost efficient, and they stay within our $100 budget. So for our motor, the motors are typically going to be around $20 to $40 each. 40's on the higher end. The vacuum itself is going to be $30. The CPU is a little bit lower end, but that's going to be $20. The battery is going to be $10. And the transmitter/receiver is going to be $7. You can find those for 50 cents, but we decided to go a little bit higher end on this just to maximize efficiency.
So work breakdown structure, this would be for the spring. So we'd want to basically start off with doing unit tests and then also programming the CPU. And once we completed those, we'd be able to move on to integrating these different components together. And through testing those integrations, we're able to improve and make sure that all these components work separately. And then near the end of our work breakdown, we assemble it and then also do final testing, do acceptance testing for our constraints, and then prepare for presentation.
For the test plan for this project, we're going to have 3 different types of testing. So for our unit testing, we're going to be testing the motors and the vacuum itself. For the integration testing, we're going to be testing the receiver/transmitter, the motor, and the vacuum. And for the acceptance testing, we'll be testing pretty much everything. So the battery, the vacuum, the efficiency, and the speed.
And so this is one of our unit tests. This is the unit test for the motors. We basically set up the motors and we give them signals to move them forward, backward, and we're testing each motors and how they move and make sure that they all move with the setup we have, so that when we configure it with the CPU, that we're able to ensure that we're sending the right signals to get the motors to do what we want. For the integration testing, we integrate the receiver and transmitter. And what we're doing here is we want to make sure that we're able to send signals to the CPU from an external device and be able to get that back and interpret that data correctly. And then for acceptance testing, what we're doing here is we're testing the robot's engineering requirements. So basically, we want to set the robot fully charged in a space and just let it run for a while and make sure that it's able to run and meet the specifications that we defined in our constraints.
References.